magnetic field of 0.15 Tesla in the positive z direction is present in this region of space, and we have a triangular prism. We'd like to calculate the magnetic flux through each surface of this prism, and then we'll calculate the total magnetic flux. I have numbered each of the 5 surfaces. I also have indicated the direction of the magnetic field on the coordinate frame. Remember, the magnetic field is in the positive z direction. So then the magnetic field is parallel to surfaces 1, 2, and 3, meaning the flux through these surfaces is equal to 0. Now let's calculate the magnetic flux through the surface number 4, that's surface BEFC. The flux formula is the dot product of the magnetic field and the area vector, and the area vector points outward from the enclosed volume. So then the area vector for the surface number 4 is pointing in the negative z direction. So B is pointing in the positive z direction and the area vector is pointing in the negative z direction. The angle between the two is 180 degrees. And remember, dot product is the product of the magnitudes of both vectors times the cosine of the angle between the two vectors. So that's going to be B times A4 times cosine 180, and cosine 180 is -1. After substituting the numerical values, we get -3.75 times 10 to the -4 Weber for the magnetic flux through surface number 4. Now let's take a look at surface number 5. That's surface AEFD. This surface makes an angle with the magnetic field that is not 0 or 90 or 180, but it's something in between. It's an angle smaller than 90 degrees basically. And first let's determine this angle. Actually, we don't need to find out what that angle is. All we need is the cosine of this angle, and we can determine the cosine of the angle from the given geometry in the picture, so we don't really need to calculate that angle separately. So here's one way to find out more about that angle. Now I have my area vector A5 that's perpendicular to the area and pointing outward from the volume, right? So that area vector A5 is basically perpendicular to segment DF. It's easier to see that way. And then I redrew my vector B, the magnetic field vector, right next to A5, so we can see the angle in between, right? So this is the angle we're looking for. In the formula, we need the cosine of this angle. Let me name the inner angles of the triangle DCF. So C, corner C, that's 90-degree corner, right? That's the coordinate frame's corner. So I'm going to call this angle alpha, and this one I call beta. Alpha and beta add up to 90 degrees. Now, if this angle is alpha, this is also alpha. And then here we have another 90-degree corner right here, right? Between the area vector A5 and segment DF. So then that makes this angle beta. And that's the angle that goes into our equation. And we're looking for cosine beta. We can find it from the triangle DCF again, right? Cosine of beta is equal to segment CF, which is 5 centimeters, divided by the segment DF, which is the hypotenuse of that 90-degree right triangle, which is 12 centimeters, right? So 5 divided by 12 is cosine of angle beta, and that's what goes into our calculation of magnetic flux through this surface. And here's a numerical calculation for the magnetic flux through surface 5. It's equal to the magnetic field strength times the area AEFD, which is 5 centimeters times 12 centimeters, times cosine of the angle beta, which is 5 divided by 12. And we get 3.75 times 10 to the -4 Weber. This is the same as the flux through surface 4 with a positive sign. And what do we get when we add up all the flux values? The first three were equal to 0, and flux number 4 and 5 cancel. So the total flux through the entire volume, the entire closed volume, is equal to 0. Is this expected? Yes. Remember, magnetic flux through any closed volume is equal to 0. And this is related to the fact that there are no magnetic monopoles.